Hello. Okay, in this video, we're gonna learn what's called Euclidean algorithm to compute the greatest common divisor of any pair of integers. Um, and after that, we're gonna solve certain types of integer combination problems. Okay, let's jump right to it. All right, so we're gonna start with the definition of greatest common divisor. So if you have two integers a and b, and they can't both be zero, if they are, then you're just gonna say the greatest common divisor is equal to zero. But if at least one of them is not non-zero, then GCD is defined as the largest natural number that divides both a and b at the same time. So by convention, well, anything divides zero. So GCD of 0 and 0 would be infinity. I guess that's the only thing that makes sense. But by convention, it's actually not a good definition. If you set it to 0, everything else will work out. So that will be the default for 0 and 0. So it's basically the number that's kind of shared divisor between two pairs of numbers. So if you take a GCD and divide both of the numbers by the GCD, then you get what's left over is going to be relatively prime. So that's how it's usually used. All right, so let's prove a theorem about this that's going to be useful for us. Okay. The set of integer combinations. So when I say integer combinations, I mean linear combination where the coefficients are integers. The set of integer combinations between the integers a and b are the same thing as the set of multiples of the greatest common divisor between a and b. So let's prove that. Okay, so just as a shorthand, I'm going to start using D as the GCD between A and B. So this is equivalence of two different sets. So integer combinations of A and B and multiple of GCD. So let's give name to these sets. So the integer combination of A and B we're going to call S. So S consists of RA plus SB, where R and S are integers. These are all the integer combination we can create from these two integers. The multiple of GCD is going to be T. Okay, so to show that two sets are equal to each other, you have to show that each of the set is a subset of the other. So let's do that S is a subset of T direction first. We know that D divides both A and B. So that's another way to say A could be written as some integer K times D, and B could also be written as some integer L times D. Okay, now let's look at integer combination of A and B. We're going to replace A with K times D because they're the same thing, and we're gonna replace B with L times D. Then both of these terms have D in it. So let's factor those out, and we're left with MK plus NL times D. But D is the GCD. So what this means is that it's part of the set T, right? It's D times something. It's a multiple of the GCD. So that therefore, anything when S could be written as multiple of the GCD. Let's prove the other direction now. So we want to show that any multiple of GCD could be the integer combination of A and B. Okay, so to go the other direction, let's say D is the integer combination of A and B. Okay, so we could divide both sides by D and get a relatively prime pair of numbers. And we know that if we have relatively prime of numbers, then we could get an integer combination of 1. So we can find m and n such that the integer combination equals to 1. But from here, if we multiply both sides by d, then the denominator on this side will cancel out, and we'll get d on the other side. So we'll get ma plus nb is equal to the greatest common divisor d. And we're supposed to be able to get any multiple of that GCD. So if you multiply both sides by k, you can write k times d as integer combination of a and b here. So we went the other direction. So now any t could be written as integer combination. So we went both directions. These two sets are equal to each other. I hope that made sense. Okay. Let's move on to Euclidean algorithm. Okay, so this is a really useful algorithm. It turns out that, like, well, the way to compute GCD is easy if you have prime factorization of both things already. So for example, let's see, 2 times 3 squares, this is 18, and this is 120. Okay, if you're trying to compute the GCD of 2 different numbers, and you already know the prime factorization, all you have to do is look at the multiplicities of each prime numbers and look at the minimum of each multiplicity. So let's see, 18 has 1 copy of 2. 120 has 3 copies of 2 that divides into it. 1 is less than 3, so the GCD is going to have 2 to the 1. 18 has 2 copies of 3 that divides into it, and 120 has 1 copy of 3 that you could divide into it. 1 is smaller than 2, so that's in the GCD. 18 has only those 2 prime as a factor. 120 has also 5 as a factor, but it's not in 18. So the minimum between 0 and 1 is going to be 0. So anytime you have 0 copies of a prime, you don't write that in the GCD. So the GCD of 18 and 120 is going to be 2 times 3, or just 6. So you just look at the smaller exponents and collect those. That's all you have to do. But it turns out that trying to come up with a prime factorization, so this was a smaller example, so we were able to do it. But in general, if you're working with larger numbers, factoring could take quite a long time. In fact, if you're a computer scientist, maybe you are already aware that factoring is so difficult sometimes that it's a basis for encryption algorithm. So in general, trying to come up with a prime factorization is actually a longer way to compute the GCD. There's actually a faster way to do it, much faster way. And that's called the Euclidean algorithm. So let me describe that. Okay, so I'll just do it by example. So I just came up with 2 random 3-digit integer. And once you follow this algorithm, I encourage you to try your own as well and convince yourself that you could do this. All right, so what you do is you always, what I'm gonna do is I'm always gonna write the larger number to the left and the smaller number to the right. So the first step is to write the larger number. And what I'm going to do is I'm going to subtract the largest number of copies of the smaller number that I could take away from the larger number. So I think 5 times 132 is less than 723, but 6 is too big. So I could subtract 5 copies of 132 from that. And you might need a calculator for this one. So 723 minus 5 times 132. I'm going to get 63. Okay. And now what I'm going to do is I'm going to try to do the same thing with these two numbers. So 132 is now the larger number. So I'm going to write 132. And I'm going to look at the largest number of copies of 63 I can take away from this. And I could take away 2 copies of 63. So 132 minus 126 is going to be 6. And now I'm going to do the same thing with these two numbers. So 63 minus the largest number of copies I can subtract from 63 is going to be 10 copies of 6. And 3 is left. Once you have these two to be multiple of each other, you can kind of stop. But let me just kind of go one more step, just for the sake of completeness. So 6 minus 2 copies of 3, okay, you'll get 0 at the end. So when you get 0, you completely stop. And the number you got before 0 is going to be your GCD. So 723, 132 is going to be 3. And not only that, this Euclidean algorithm, if you kind of look at what you did, you can kind of reverse engineer the integer combination that gives you this number 3. So let me kind of go backward. So what I'm going to do is I'm going to look at the second from the last equation that has GCD on the right-hand side and write it down. So 63 minus 10 times 6 is equal to 3. I'm not going to do anything to the right-hand side, but what I'm going to look at this number 6. And I'm going to substitute 6 using the previous equation. So 6 is equal to this thing right here. So I'm going to substitute that into the 6 there. So I'll have 63 minus 10 times 132 minus 2 times 63. And all that is equal to 3. And if you look at this, I see 63 appearing 2 different places. So I'm going to multiply everything out and collect like terms. So I have negative 10 times 132. And let's see, negative 10 times negative 2 is positive 20. And then there's 1 extra copy of 63. So 21 times 63 is equal to 3. Okay. Now what I'm going to do is I'm going to look at the equation before the 6. Look at the equation with the 63 on the right-hand side. And I'm going to substitute 63 with what's on the left. So let's see, 21 times, instead of 63, I'm going to write down 723 minus 5 times 132. And all that is still equal to 3. And now I'm going to multiply out the 21 and collect like terms. So there's 21 copies of 723. And let's see, so 21 times -5 is going to give me -105. And there's also -10 copies of 132. So minus 115, 132, equal to 3. So notice now I have an equation that gives us the GCD as an integer combination of the two numbers that we started with. Some multiple of this plus some multiple of this is equal to the GCD. You watch me walk through this. It kind of takes a little bit of practice to do this. So what I encourage you to do is pause this video, take out a sheet of paper, come up with two random 3-digit numbers. Maybe you could roll a die or just make one up, and then see if you can go through this process to first compute the GCD of those two pair of numbers, and then use those equations that you've written down to reverse engineer an integer combination that gives you that GCD using the original two integers. So please try it out. Okay. So now we actually have a general method to solve for integer solutions to linear equations. So let's say we have an equation that looks like integer combinations of two numbers a and b, and I want to get the number n. We can completely solve these type of problems. So we're gonna do it in 3 steps. So first thing is to recognize if it has a solution at all. Here's an example problem. 6x plus 15y is equal to 79. We know from the theorem earlier that any integer combination you can get has to be multiple of the GCD. But in this case, so I'm looking at the 6 and 15, and the greatest common divisor for both of those is 3. 3 divides 6, and 3 divides 15. But 79 is not a multiple of 3. So we know that this is impossible. So it has no solutions. Okay, so you can recognize a problem that you can't solve pretty quickly. Let's look at a problem where you could solve, right? So 6x plus 15y equals to 99. So 99 is a multiple of 3. So there is a solution. But it actually turns out that whenever you can solve an equation like this, there's infinitely many different solutions. So let's see if you can write down all of it. All possible combinations of x and y that gives you 99. All right, so the first thing to do is to, once you get the GCD between the two integers we're looking at, you could divide both sides of the equation by the same number. So we know the GCD is 3 here. So we're gonna divide 3 to both sides of the equation. So now we get a reduced equation, 2x plus 5y, where the two numbers 2 and 5 are now relatively prime. And on the right-hand side, 99 is divided by 3, so we get 33 there. All right, so the next step is to do Euclidean algorithm, but 2 and 5 is actually pretty small, so it's actually pretty easy to do that. But Euclidean algorithm gives you, remember, the integer combination of these two numbers, so that it gives you that GCD between the two. And since now that we've reduced the equation, you have relatively prime numbers. So the GCD in that case is going to be 1. So you should be able to write down 2x plus 5y equals to 1. Or at least one solution to that. And once you can solve how to do that for 1, you could just multiply that to both sides of the equation. So if I want to solve that equals to 33, then I can multiply 33 to each of these numbers and get this new equation. 2 times negative 66 plus 5 times 33 is equal to 33. Okay, so we found one solution to it. The solution is when x is equal to negative 66 and y is equal to 33. If you want a full set of solution, what you do is just realize, so 2 and 5s are relatively prime to each other. But if you take the product of the two, so 2 times 5 is equal to 10. What you could do is every time you remove 5 copies of 2, you could add 2 copies of 5 into the second equation. So what I mean by that is this is the coefficient of the 2 here. We're starting with negative 66. And every time we add 5 times 2, 2 is being multiplied to that. So I'm going to write the 5 here. Then you have to subtract away 2 copies of the 5. So the coefficient of the 5 is going to be decreasing every time the coefficient of the 2 is increasing by 5. And you could like add and subtract, you can move it in either direction. So the only thing that matters here is that the plus and minus sign is the opposite here. And this k could be any integer. So as long as you're moving copies of 2 times 5 from one term to the other term, you maintain the same sum of 33. So that's how you can get the infinitely many different solution of that equation. I hope that made sense. I want you to encourage you to jump right to homework and solve the problem, exactly the problem that I just gave you right now. I want you to be able to solve these problems. Okay, that's it for this week. I will see you next week. Bye.